Welcome everyone. In this video we will prove Kepler's third law, which states that the square of the period is proportional with the cube of the radius. Of course, I need to give some context for you to be able to understand what this proportionality means. So this law, which I said is Kepler's law, Kepler's third law actually. This law is a law for an satellite, for example, or a planet orbiting around another celestial body. Okay, so maybe we have a planet like this with mass capital M, and we have a satellite or another planet, a moon perhaps, orbiting it with mass small case m, and the radius is r. So I am drawing it from the center of mass of one object, one mass to the other. So that is r. Well, as I said, we will prove this law, and actually we will not only prove this proportionality, we will also find the proportionality constant. So at the end of this video, I will actually give you an equation, which is Kepler's third law. And you perhaps saw that equation already on the thumbnail, but anyways, at the end you will see it, so stay tuned. So how can we carry out this proof? Well, the key here is we will say that F net, the net force, will be equal to F centripetal, because we are interested in a circular orbit. This law also holds for elliptical orbits, like the one Earth follows around the Sun, but I won't do the proof for that one in this video, and the equation and the proof for it is very similar to the one that we are about to do. So as I said, F net is equal to F centripetal. And notice that I am not putting arrows, so this means their magnitudes. Well, how can we proceed from this? We know that F net is the force of gravity in this case, and F centripetal is still staying here. So for the force of gravity, we will use Newton's law for gravitation, which says that to find the gravitational force between two objects, you have a proportionality constant, the universal gravitation constant, I believe its name is. Then you have the first mass multiplied by the second mass, all divided by the square of the distance between them. So we have this, which comes from Newton's law, as I said, and this is equal to the centripetal force. Well, the centripetal force, I proved this in a previous video. It is equal to mv squared divided by r. Or I might have proved that v squared over r. This part is centripetal acceleration, and if you multiply it with m, you get the centripetal force, right? Because F is equal to ma. So we got this. Now, what I want to do is, I want to mention that V is equal to omega times r. R here is the radius, V is the speed, and omega is the angular speed. It is the angular velocity. So if we substitute this to the centripetal acceleration, we have m, and instead of v, I am writing omega r. It is squared, so we have omega squared r squared divided by r. We see that 1r cancels here, so we have m omega squared r. This is great. Also, we see a great thing. We see that if we look at this and this, we see that small case m cancel. What does this mean? This means that the mass of the object that is orbiting the other object, the lighter mass actually, the one that is orbiting the heavier mass, it doesn't matter. Its mass is, as you can see, cancelled. So if you have a heavy planet, if you have a small satellite, a big satellite, it doesn't matter for our calculations. That's what the cancellation of small case m means. So if I am going to continue here, we have that gm divided by r squared is equal to omega squared times r. Now, at this point, I want to divide both sides by r, so we get that gm divided by r cubed this time is equal to omega squared. Well, if we think about omega now, and I'm going to write it in orange, omega is, as I said, angular velocity. So it is simply the change in the angle, change in radians, divided by change in time. Well, if we are interested in finding the period, because that's what we are trying to do, we are trying to prove Kepler's third law, then for time we should have period, which simply means the time that it takes for the orbiting object, whatever that is, the time that it takes to complete one full revolution. So if it starts here, it goes all the way here, and it arrives here, and when you look at your time, the time that passed is your period. So, what is the angle that we cover in one period? It is one full revolution. What is one full revolution in radians? It is just 2 pi. So, we can substitute 2 pi divided by t for omega in our equation, in this equation, I mean. Which I am going to do with red, actually. Yeah, let's make it with red. So, we have gm divided by r cubed. Now for omega squared, we have 2 pi divided by t squared, right? So I am just going to write it as 4 pi squared divided by t squared. All right, I just substituted 2 pi divided by t for omega, and then I squared it to get 4 pi squared divided by t squared. Now, if we solve for t squared, look what we get. To solve for t squared, we multiply both sides by t squared, and then we divide by, we first multiply by t squared and r cubed both sides, so we have t squared gm is equal to 4 pi squared r cubed. Then if we divide both sides by gm, then we will get that t squared is equal to 4 pi squared divided by gm r cubed, and this is actually the period of a satellite, for example, orbiting the Earth. And this is Kepler's third law. As you can see, t squared is proportional with r cubed, and this thing 4 pi squared divided by gm is our proportionality constant. I hope you found this video helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care. Just a quick addition, if you wonder why v is equal to omega r, I realized that I didn't go over this in the video. If you wonder how this is correct, let me show you. So I said that v is equal to omega r. Omega r. Well, this can be derived as follows. We know that v is the speed that the satellite is traveling in the orbit. So v is the distance that you travel divided by the time. By definition, that is what speed is. So what is the distance that you travel if you think of a full period? Well, you get 2 pi r, right? This is just the circumference of the circle. And as I said, it is for a full period, so you just have t. And as you can see here, we have 2 pi divided by t, which is just omega, and we still have r. So that's why v is equal to omega r. And you could do this instead of thetas and t's. You don't need to use 2 pi and t, the period, to do this proof. I hope this clarifies if there was a confusion. And thank you for watching the video. Take care again.